Hey guys, hi, welcome back to my channel Net Physics. And if you're watching this video for the very first time, then I would request you to please subscribe to my YouTube channel. So in this video we shall discuss the questions of nuclear physics, and these questions are not from the CSI net examinations as the previous videos all that I have uploaded. This time we will discuss the questions of JEST. Okay, so in this video I shall cover all the questions from 2013 to 2019. Okay, and now most probably there are not that much questions of nuclear physics in the JEST examination compared to the initial years. And also I'd like to say you that you should see through all the questions and the patterns, because somewhere the patterns of the questions are changing. So let's start the video and with our first question, which is from JEST 2013. So what is the question here? It is given here, uranium-238. Okay, it is decaying with a half-life of 4.51 into 10 to the power 9 years, and the decay series, it eventually ends at lead, that is Pb206, which is stable. So whenever we know that whenever any element, okay, when it is decaying, then it is eventually going through many unstable elements. Okay, it will continue until and unless we get a stable element, right? So from uranium-238 we are getting lead-206, okay, and it is stable, and this is the half-life of uranium-238. Okay, now a rock sample analysis shows that the ratio of the number of atoms of lead, okay, 206 to uranium-238 is 0.0058, right? This is the ratio of the numbers of atoms of lead-206 to uranium-238, and the ratio is 0.0058. So now what it is said, that assuming that all the lead, it has been produced by the decay of what? Uranium. Okay, here it is said all the uranium, it is decayed and it has produced lead. Okay, and all other half-lives in the chain. Here we have to assume that all other half-lives during this decay, it is neglected, and we have to find out the age of the rock sample, and that is in years. Okay, so here we are having the 4 options. So firstly we will see the given conditions here. So firstly we will see that the uranium-238, it is decaying into lead-206, which is given in the question, and the half-life of uranium is 4.51 into 10 to the power 9 years. Firstly, according to the question, if we see the question and if we analyze this, then what you will say, that initially uranium is N0 number of uranium is there, okay, and lead is 0, because this is the initial stage of decay where uranium is N0 and lead is 0. But after time t, NUT is the number of uranium, and NPB, that is NPB, which is PB is giving the symbol of lead, okay, NPB, it is the number of lead at time t. Now since initially the total, okay, the total product was how much? N0. That means in this time t, okay, NUT plus NPBT must be equals to how much? N0, right? So now if we will divide both the left hand side and right hand side of this particular equation by NUT, then what we will have, this is giving us 1, this NPBT by NUT, it is equals to this. How it comes to be equals to 0.0058? Because in the question it was said to us that the rock analysis, rock sample, it analyzes that the ratio of the number of atoms of lead-206 and uranium-238 is 0.0058. So this is the ratio of number of what? Atoms of lead by the number of atoms of what? Uranium. Okay. After a time t, it is equals to this much. This is the ratio. So I have used this value here, and this is N0 by NUT. So finally what you will have is N0 by NUT. It is equals to 1.0058. Now we will see the very common radioactive law, which says that N is the number of atoms always. It is equals to N0 e to the power minus lambda t. So here N, with this equation we will write for NUT. So it is what? Number of uranium, okay, after time t, okay, uranium atoms after time t, it is equals to what? N naught e to the power minus lambda t. Now here what we will see, this N naught will come, we will come, okay, here, that is N naught by NUT. We will use this particular value. So we will find the ratio of N naught by NUT. It is equals to e to the power lambda t from this particular equation. Now when we will put the value of this particular term here, 1.0058 is equals to e to the power lambda t, and we all know lambda is equals to what? Log 2 by t half, okay, which is equals to 0.693 by t half. So this is what we have substituted here. T is as it is here. Now log of what? How it comes? Log, I would say here, because taking the exponential we all know, okay, removing the exponential, which will give us what? Log here in the left hand side, and in the right hand side we will have the exponential terms as it is, which is 0.693 by 4.5 into 10 to the power 9 into with the time t. So when you will calculate this, all the things, okay, taking the log of this particular term and multiplying this 4.5 to the right hand side and again divided with your 0.693, it will give you 0.3755, and you have to make it into 10 to the power 6 years, okay, then it will give you 37.55. so which is approximately 38 into 10 to the power 6, okay, which is approximately this particular. So the correct answer will be how much? The option A, that is 38 into 10 to the power 6 years. This is the age of the rock salt sample, okay. So this is very simple. The only thing is that you have to just go through the simple steps without skipping. Now let's come to the next question. So the next question here is that the binding energy of the K shell electron in a uranium atom where Z is equals to 92 and A is equals to 238, it will be modified due to the screening caused by other electrons, and the second one is the finite extent of the nucleus as follows. So here we have to say what will be the change in the binding energy. It will increase, or whether it will decrease, or it will remain unchanged due to the screening caused by other electrons and the finite extent of the nucleus. So here I have marked the answer to be answer B, and how it comes, let me explain you. So now let's go to the explanation how it happens. So this is the nucleus, these are all other cells. Nucleus has positive charge and all this other cells have what? Negative charge. So binding energy will be required more, because you see when the electrons, okay, the positive charge in the nucleus will attract the negative charged electrons, that means there will be attraction, and all other all other shells have what? Negative charged electrons, okay, electrons are negatively charged in that, so they will what? Repel, okay, because the K shell electron is having negative charge. Just listen to me carefully what I am speaking, that this is the nucleus. The nucleus has positive charge and all other shells are having what? Negative charge, whether it is K, L, M, N. So there will be force of attraction, okay, between the nucleus and the K shell electron, and all other shells will have what? Repulsion, okay, with the K shell electron. So only this electron in the nucleus, the positively charged electron in the nucleus, will attract this particular electron of the K shell, and all other will repel. So we know that the binding energy is what? It is the energy required to remove the electron from the K shell, okay. So when there will be more force of attraction, then more energy will be required. But here what we will see, 3 means all other electrons are negative, means others are repelling. So due to the screening of the other electrons, it will make the electron to come out easily from the K cell, means it will decrease the binding energy. And also when we are talking about this particular electron, okay, that is the nucleus is positively charged, we know that the nuclear forces are what? It are working up to a certain these are short range force, okay. So the effect of this electron, okay, the effect of this attraction will be also up to a certain range, but after a certain range it will not work, and that will also what? That will also allow the electron to come out very easily from the K shell. So as a whole, what we can see, that the binding energy of the K shell electron, it is decreasing due to the screening caused by other electrons, and also it is decreasing due to the finite extent of the nucleus. So it's very clear to all of you. This is very simple concept. So now let's come to the next question. So here the next question is from JEST 2014, and here it is given that in the mixture of isotopes normally found on the earth, okay, at the present time uranium 92-238, it is having an abundance of 99.3%, and uranium 92-235, it is having abundance of 4.7%, and the lifetime measured of these two isotopes is 6.52 into 10 to the power 6 years and 1.2 into 10 to the power 9 years, right? So we have to assume that initially, okay, both the isotopes were equally abundant, and we have to estimate the age of the earth in years. So here we are having 4 options. So firstly we will write what is given. It is given initially, okay, these are the two isotopes given. Initially we are considering that the total number of atoms to be n naught, okay, so this isotope will be n naught by 2 initially, because both are equally abundant, so both will be what, half of the total, so both are n naught by 2. And after time t we are considering the number of atoms to be nt, total number of atoms to be nt. So after a certain time it was given that this isotopes is how much, abundant 99.3, which I have written 99.3 by 100 nt, and this is 0.7 by 100 nt. Now the lifetimes tau 1 and tau 2 is given 6.52 into 10 to the power 9 years for this particular isotope, and 1.2 into 10 to the power 9 years for this particular isotope. Now what we will see the law of radioactive, okay, decay, which is n is equals to n naught e to the power minus lambda t. Lambda is equals to what, 1 by tau, which is written here e to the power minus t by tau instead of e to the power minus lambda t. Now we will write this radioactive decay law for both the isotopes. So the first one will be 99.3 by 100. I have just substituted the value of n and n naught. N naught is the initial number of atoms and n is after time t. So it is 99.3 by 100 nt equals to n naught by 2 e to the power minus t. This is the value of tau 1. Similarly 0.7 by 100 nt equals to n naught by t e to the power minus t, 1.2 into 10 to the power 9 years. This is the value of tau 2. Now what we will see, we will divide equation 1 and 2 because we have to find the value of small t, right? So on dividing, what we will have in the left hand side 993 by 7, okay, rest I have just simplified it, okay, the left hand side, nt and nt will get cancelled, equals to e to the power t, it will be how much, 1 by tau 2, this divided by this, so this will become the first term, 1 by tau 2 minus 1 by tau 1. This is basic simplification you can see into it, okay. That is log of what, exponential on removing will give us what, log 993 by 7 equals to t 1 by 1.2 minus 1 by 6.52 into 10 to the power minus 9, which is taken in the numerator from the denominator. And as a whole, when you will calculate this particular term, okay, you will get 7.28 into 10 to the power 9 years approximately. So when you will see the answers out of the 4 options, you will see that the approximate answer is 6.0 into 10 to the power 9 years. Okay, these are questions. These questions are not giving the exact value. It will give you the approximate, because you can see it is 10 to the power 9, right? It will be 10 to the power 9 years. So we are having 2 options of 10 to the power 9, and it is 7 point something. That will be what, 6. You can see the calculation once again on your own. There you may get varied something, but the option is option A. So now let's come to the next question. The next question is from JEST 2015, and the question is that the stable nucleus that has 1/3 the radius of osmium 189 nucleus is. So these are the 4 options. We have to find out the radius, okay, we have to find out the stable nucleus, okay, which is having the radius which is 1/3 of this particular nucleus. So we know the very basic formula of nuclear radius. R is equals to what, R naught a to the power 1/3. This is the radius of osmium considered to be here, okay, of this particular nucleus. And we will consider R1 to be the radius of the stable nucleus. So R1 is equals to what, 1/3 of R, the radius of the stable nucleus. It is given 1/3 of this particular nucleus. Now when we will substitute the value of R here, it will be what, R naught a to the power 1/3. The value of A for this particular nucleus is how much, 189, right? So R1 is equals to what, R naught A1 to the power 1/3. This side, in the right hand side, we have 1/3 into R naught 189 to the power 1/3. So this R naught and this R naught both are constant, and it will cancel out, and we will have A1 1 to the whole to the power 1/3 and 1/3 189 whole to the power 1 by 3. So taking this particular 1 by 3 to the right hand side, we will have A1 is equals to what? 1 by 3 cube, that is 27 into 189, right? And on cancelling these two terms, we will have 27 7 times. Okay, 27 7 is 189. So A is equals to what? A1 is equals to 7. So the stable nucleus will be lithium 7. So the correct option is option A. So now let's come to the next question. The next question is this is a reaction, okay, and this particular reaction is what? Forbidden. Why it is forbidden, we have to see. The first option is lepton number is not conserved. The second is linear momentum is not conserved. The third one is angular momentum is not conserved, and the fourth one is charge is not conserved. So here this is the reaction. This is a positron, the other one is electron, and it is giving a what? Gamma photon. So when you see here, basically we will see what is not conserved here. So you see this is a positron, this is coming from this particular direction, this is the electron which is coming from the other direction. So the total momentum will be how much? The total linear momentum, it is equals to what? 0. That is pi, it is equals to what? 0. Now it is giving what? A gamma photon, right? So which will, a single photon is there, so it may go in any direction. So the momentum, the energy is equals to what? Pc, right, in this case. And the momentum, final momentum, it is equals to what? E by c from this particular equation. That means it is not equals to 0. So if you see here, the linear momentum is what? It is not conserved in this particular case. So this equation is forbidden because in this question the linear momentum is not conserved. One thing I would like to add here, that it would be conserved if there would be one more gamma photon. Okay, if it would give one more gamma photon, then this would be a allowed. Okay, this is be a allowed reaction. So now let's come to the next question. The next question is from JEST 2016. So here it is, the half-life of a radioactive nuclear source is 9 days. This is the half-life of a radioactive nuclear source, and the fraction of nuclei which are left undercaved after 3 days is. So we have to find the fraction of nuclei which are left undercaved, and that is also after 3 days. So half-life is given how much? 9 days. Initially the total number of atoms were n0. So according to the radioactive law, the remaining is denoted by n. So n is equals to what? n0 e to the power minus lambda t. So n by n0 is equals to what? E to the power lambda t. N by n0 it is equals to lambda can be written as what? Minus log 2 by t half into it t. So log 2 is as it is, t half is how much? 9, and small t, it is equals to what? 3 according to the equation. This is the time under which we have to find how many fractions of the nuclei were left caved. So n by n0 is equals to what? If you see this 3 will cancel what? 9 3 times. So we will have what? Minus 1 by 3 log 2, which can be written according to the logarithmic properties. It can be written as e to the power log to the power minus 1 by 3. This log and e, it will get exponential, we cancel the log, and we will have 2 to the power minus 1 by 3. That means n by n0 is equals to what? 1 by 2 to the power 1 by 3. So the correct option is what? The correct option is option D. So this is very simple question. I am repeating again and again. You can see the basic radioactive formula is used, the basic nuclear radius and all these things. So now let's come to the last question. The last question is from JEST 2019. So here the question is, a cyclotron, it can accelerate deuterium to 16 mega electron volt. Okay. So if the cyclotron is used to accelerate alpha particles, what will be their energy? We have to find the energy. Okay, here it is given that a cyclotron, it can accelerate deuterium, okay, to this particular energy, this much energy. Okay, and if the cyclotron, it is used to accelerate alpha particle, what will be the energy we have to find? We have to take the mass of the deuterium to be twice of that of the mass of proton, and the alpha particle's mass is taken to be 4 times the mass of proton. So these are the 4 options. So firstly we will write what? Mass of deuterium is what? Twice the mass of proton, and we know for deuterium we are having 1 positive charge, and the mass of alpha particle is what? 4 times the mass of proton, and alpha particles are having what? 2 positive charge. Okay, so it is twice E. Now we have the formula, okay, the energy, okay, of a particle accelerated by a cyclotron. It is given E is equals to Q square B square R square by 2m. So here you can say B and R, these are the constant terms in case of cyclotron, so it will not change. And so energy for deuterium, it is equals to what? E square into with what? it is E square because the charge is what? E in case of deuterium, into with B square R square by 2 into with the mass is twice of proton. And in case of alpha particle, it is what? 4E square because it is 2E. So it will become what? 2E whole square means 4E square, into with B square into with R square by twice into with 4 of mass of proton, because the mass of alpha particle is 4 times the mass of proton. So this will give you how much? 4 and 4 will get cancelled, and you will have E square B square R square by twice the mass of proton. Now when you will see, you have to find the energy for the alpha particle. So we will do ED by E alpha, the energy of deuterium divided by the energy of alpha particle, which is equals to what? This term into with the reverse of this term. You can see on this term E square B square R square, this term will get cancelled automatically. M, mass of proton, the masses will get cancelled, and this will be equals to what? 2 to the 4. And finally you will have what? Energy of deuterium by energy of this alpha particle is equals to 1 by 2. And energy of alpha, okay, E alpha, energy of the alpha particle, it will be what? Twice of the energy of deuterium, that is 2 ED. So the energy of the deuterium, it was given in the question to be 16 mega electron volt, and it will give you the energy of the alpha particle to be 16 into with 2, that is 32 mega electron volt. So the correct option is option C. So this is really very easy and very basic concepts are applied here. There is no rocket science to do in these basic questions. Don't get nervous that the questions of JEST are very tough. They are not at all tough. The only thing is that you need to know the basic formula and the basic things, that how you have to find it. Don't go to the highest height, okay, don't go to the top of the ladder, just go to the basic, the first step, okay, the first line of the ladder, then you can solve it very easily. And if you're finding my video helpful, do share with your friends. Also comment in the comment section if you want me to make any changes, or if you want or if you have some questions that you want me to solve, then you can mail me in the email ID given. So that's all in this video. Thank you so much. Have a good day.